In this video, we are going to finish up our discussion on Dijkstra's algorithm. So I wanted to point out a couple of things about Dijkstra's that we didn't go over last time. So last time we went over the algorithm and thoroughly traced it so that we can understand the idea of it. It's very similar to breadth first search, but it adds this priority queue, etc. So let's point out a couple things about the algorithm that are important to think about. So first is that when you pop the priority queue, one thing is that as soon as you pop something off the priority queue, you have found the shortest weighted path to that vertex. So basically on this step of the tracing, as soon as you actually get that node popped off, you are done and have found the shortest weighted path. So if you are looking to use Dijkstra's to find the shortest weighted path from one node to a very specific node, then you can stop the algorithm at this point. The Dijkstra's algorithm that I showed last time was fully finding the shortest weighted path to each node from a starting node. So that's the first thing I wanted to point out. Let's talk a little bit about some of the modifications that were done on the Dijkstra's algorithm as it's presented in, for example, Zybooks. The first thing is that we added this visited vector. We added this for a couple different reasons. One, it's really good for grading and debugging purposes. It can ensure that you're actually applying the algorithm correctly because we know that you have visited the nodes in the correct order. It's not traditional in Dijkstra's algorithm, so you won't see it. All it does is it adds this step here to actually add the node to the vector and then return it here. So that was something that we did. And then we were able to use this modification in order to do some checks before we go through the mess of visiting all of the neighbors. So for example, if the current node's distance is infinity, then we know we've actually finished walking through all of those nodes, and so we can break. If the current node has already been visited, we can actually just skip this iteration. We don't need to go. What this does is if you don't have this modification in here, so if you don't have this branching option, you'll actually visit a bunch of nodes multiple times, and so that would be unnecessary to keep revisiting. And so instead of going through and completing this aspect of the algorithm for nodes that you've already visited, this can allow you to skip that. However, there's a trade-off, right? So the modification could make it more efficient, or you might think that it's more efficient, right? And so that's one option. It's added for a couple different reasons. And so the question is, what is the complexity of this additional code being added to this spot? So we're checking if a distance is infinity, we're checking if the vertex has already been visited, and then we're also adding something to a container. So go ahead and pause the video and think about it for a minute, what the complexity is, and see some of these options here, and then come back when you're ready. So the first option is the code is 01, no impact on time. Second option is it's 01, but it does increase space complexity. So as far as this one here, it does increase space complexity to add the visited set, but nothing else. The visited vector, but nothing else increases space complexity. So this one just says it's O log n, and this one says it's O(n). So the question is basically, is this 1 log n or n complexity? So the first check is going to be 01. You're just basically checking if the current node's distance is a value, so that's a constant. This is also 01, adding something to a vector, and so the question is here. So checking if a current node has been visited depends on what container you're using to store the visited nodes. So if you're just using the same container here and it's a vector and it's not sorted, then you're going to have an O of n complexity here. Or if you create another container like a set, or you keep it sorted in some way, then you could reduce it down to log n. Obviously, it would be possible to maybe incorporate some hashing to reduce it to O1, but in general, it's probably going to be a log n or n complexity operation. So, whole point here is that it's not free. So, it is questionable whether or not it actually does increase the efficiency, improve the efficiency of the algorithm overall. However, it does allow us to have one more advantage. So Dijkstra's algorithm is normally limited to non-negative weights. So it does not allow graphs with negative edges. And actually, the paper that originally presented Dijkstra's algorithm has the title Single Source Shortest Path Algorithm for Arbitrary Directed Graphs with Unbounded Non-Negative Weights. So the original design of the algorithm is that it does not work for negative weight edge. The reason is because if you have a negative weight, like here, your algorithm is never going to terminate because you can continue to cycle through a negative edge infinitely, and your total cost will continue to keep going down, right? Your weighted path will keep going down. So this modification allows, in addition to some other things, us to be able to handle negative weights, basically. It's not necessarily going to, the algorithm won't necessarily find the shortest weighted path with the negative weights. It doesn't really work like that, but at least it won't infinitely cycle on negative edges. So that's a little bit about some of the modifications. What we're going to be talking about today is the second part of Dijkstra's algorithm. So thinking back to what we did in the last video, we were able to determine the shortest weighted path, like the actual value was 154 from G to F on this particular graph, for example. But we did not, in our algorithm, have anything that was keeping track what the path actually was. So we know that it's GECDF for starting at G, ending at F. But if you go back to the algorithm and look, you'll realize that there was actually nothing in place that kept track of that. Nothing was actually storing that. And so we don't have any way of knowing what the path is as is. Last time we presented this idea of a spanning tree and just kind of brushed it off and just like, oh, this is, but the spanning tree is actually the key to keep track of these paths. So we're going to go through what the spanning tree is and how we can use it to keep track of paths. And I hope when I showed it last time you saw it and you were very confused by these numbers because they don't obviously make sense at first look. So we're going to store the paths in this tree-like structure. And it's really cool that Dijkstra's algorithm has this structure in it because at the time that Dijkstra came up with this algorithm, all we had were arrays. And so this tree was conceptually the idea, but it is stored as an array. So this tree is able to represent all of the paths, all of the shortest paths from G to every other node in the graph. So we can see that if we wanted to get to E, the path would be GE. And the distance that we found would be 100. If we wanted to get to H, this spanning tree would show us that the shortest path would be GEH, and the distance would be 160. If we wanted to get to C, this tree would show us that the shortest weighted path is GEC, and the distance is 120. If we wanted to get to D, this tree would show us that the shortest weighted path is GECD, and the shortest distance there is 127. So that's what the spanning tree does, and that's the whole concept of the spanning tree. So the distance is just on the edge immediately before the node that you're trying to get to, and then the path is the only way to get from the starting node to the node that you're trying to find the shortest path to. So that's not too hard to understand once you see it. I mean, it's kind of tricky that the weights on the edges as drawn don't add up to the path, right? So if you want to get to C, it's this, not 220. But other than that, it's actually pretty easy to interpret the tree and find the path. If I want to get to F, well, the shortest weighted path to F would be G, E, C, D, F. But that's not how it's stored. Dijkstra came up with a way to store it inside of an array. It's called a predecessor array. And so this is what it actually looks like to store this spanning tree in an array. At first look, it's pretty hard to see how this works, but after some examples, I think you'll see the way that this works. So let's start with, let's do D. So how does this predecessor array tell us that the shortest weighted path to D is GECD? We can see it on the tree because trees are very visual. We know what it is because all of the shortest weighted paths are written here. But how does the predecessor array tell us that? Well, we start with just going to D in the vertices array, and we use the predecessors array to back out of this path back to G. So we start at D, and the predecessor array tells us that a predecessor of D is C. Then we take C and we go into the vertices array, and we go and use that to find its predecessor. So C's predecessor is E. Then we go to E's in the vertices array, and we go into its predecessor, which is G. So by starting off in the predecessor array and backing out until you get wherever you're looking for, so we're looking for G in this case, the predecessors array can back you out and find the shortest weighted path, which is really cool and really, really memory efficient in storage. So let's try another example. So let's go ahead and do H. So let's find the shortest weighted path to H. We know it's going to be GEH. We can see it on the spanning tree, but how does the predecessor array get us there? So we're going to go to H, and its predecessor is E. Then we'll go to E, and its predecessor is G. And we've reached D, so we're there. And as you can see, the distance of each is just going to be stored in the distances array. So if you want to know the distance to B, it's 127. If you want to know the distance to D, it's 127. So that can be seen in the parallel array in the distances array. So that's how the predecessor array works. Let's try it with another example. So let's try it with this example here. So what's the path to Seattle? So we're trying to get to Seattle. So we know that that's where we're going to start. So I'm going to put Seattle on first, and so I'm going to go to Seattle in the vertices array and then go to its predecessor. So its predecessor is LAX right here. So we know we're trying to get to Seattle. We can get to Seattle from LAX, so that's up by 1. One of the things you might be thinking of, well, how do we know where we're coming from? Well, because we have a predecessor array, we can see here that Midway is actually the starting point because it doesn't have a predecessor, so we're trying to get back to Midway. So then we're going to go to LAX. LAX's predecessor is Dallas-Fort Worth. So we're going to put that on next, and we can get to LAX from DFW. Now we go to DFW, and we can get to DFW from O'Hare, so we'll add that next. Now we'll go to O'Hare. We can get from Midway to O'Hare. And then once we reach a vertice that has no predecessor, we know we're done, or we just know the starting point is Midway for this example. So what I did here is, as I was working through the predecessor array to go from where I'm from, as I'm going through the predecessor array to go from one airport to the one that I can come from, I was building this stack. So we started off in Seattle, and we know we can go from LAX to Seattle, so LAX goes on top. I know I can go to Dallas-Fort Worth to LAX, so Dallas-Fort Worth goes on top of LAX. And what I did is I built a stack. So basically, one really useful data structure in decoding a predecessor array is a stack. And then what you have is, when you read the stack, because the stack will be read this way, you have the full order from Midway all the way to Seattle. So here is Dijkstra's complete algorithm. So we have added in the predecessor array here, so you can see the two additional lines added in order to keep track of the predecessor. And it's really no more complicated than keeping track of the distances. So every time you did something to the distance, you're going to now do something to the predecessor as well, and keep track of that array in addition. And then in order to interpret the predecessor array, you'll have this when you come out of the algorithm, and then you can use this interpretation, perhaps using a stack, in order to read the actual path at the end. And so that's really all there is to it. So last video we just talked about the full algorithm. We worked through everything on this algorithm that's shown here, except for what's circled in red. And then today we talked about what that predecessor array looks like and how you set that up. Predecessor array is not hard to program. You're just adding these nodes, or you're adding these elements just as indicated here in the algorithm. The tricky part is the conceptual understanding of the predecessor array. I don't think anyone, when they first look at the data stored in these three ways, would be able to tell automatically what they mean, right? So it's about interpreting it. So remember, being able to interpret it by backing out of it the way we just did, and using a stack is the perfect way to do it. Okay, that is it for Dijkstra's.